Hello everyone. Uh, I don't think everyone has joined, so let's just wait. Hi Rohi, I see you have joined it. Can you hear me?
Yes.
Hello. Yeah. I see some faintness in your voice. Is your internet connection fine or is it breaking from my side?
I don't know. I don't know.
Okay.
Maybe the internet connection is not fine.
Okay.
Am I audible now
Yeah,
clearly?
yeah, yeah.
Okay.
Okay. Maybe we should start. As you can see, I've shared my screen, but last class we discussed a few points which I have not really noted down. So let's just try to note it down. Yeah. And then we can start with today's class. So this will give a good revision as well. So the first thing we looked into is that in order to find the optimal values for theta 0 and theta 1, we need to use some method, one of which we have already seen previously. Okay, why I say this is because we have already seen a method where we calculated theta 0 and theta 1, right, using the correlation coefficient and slope and x bar and y bar and so on. So that's one way which we have seen previously, uh, which works in case of simple linear regression problems. Yeah, so this is quite normal. However, since this does not generalize beyond one independent variable, hence we move over to a better method which looks closely at rate of change and is known as gradient descent. Okay, so what we have seen in this method of gradient descent is that in this method we assume any starting value of the intercept. Okay, so we assume any starting value of the intercept. If you remember in the last session, we assumed a starting value or an initial value of the intercept, and we chose or we said that let's say that our value of theta 0, that is theta 0. Okay, let's say it is equal to 0, in which case the model or hypothesis function, okay, becomes h of theta for x is equal to theta 0 plus theta 1 multiplied by x, right? Right, so this is my y, so I can also say this is my y or y estimation. is h of theta x is equal to theta 0 plus theta 1 of x. In this case, because theta 0 is equal to 0, then this becomes theta 1 of x. Okay. Mathematically, our gradient descent exercise would find the minimization function represented as j of theta 0 theta 1, where okay j of theta 0 comma theta 1 is equal to, as we have seen, 1 by 2 times m. Okay, so this is the normalization that we have done. And then what we said, we are going to take a sum. Okay, so I'm going to say a sum from I of 1 until m. Okay, so I'll just do it like this, sum of, okay, or maybe I can say a multiplication here, sum of I equal to 1 to m of this. Just a moment, I think Sarangs is trying to join, so let me add with him. Yeah. So this part or this bracket becomes this. Okay, so this is my hypothesis, and I'm trying to minimize the hypothesis. And then what I am saying is that why not take a square? Okay, so I take a square of this, right? So this is what I'm doing. So although this is not a very good mathematical representation, but I mean, this is the best way I could write it. So j of theta 0 theta 1, this is my minimization function. Otherwise is known as, otherwise the function is also called cost function. Okay, there is a question, I believe. Let me just quickly say. No, it's fine, Saransh. We have just started and we are just looking into what we have done in the last class because we have not written down the notes. We are looking at maths. So we are trying to write down the notes, then we will start with the session. So otherwise, the function is also known as cost function. Okay, this cost function is what which we need to minimize. Okay. Now, assuming theta 0 is equal to 0, okay, for all possible values of theta 1, if we plot the cost function j of theta 1 with respect to the theta 1 value, then we get a curve similar to the structure of a you can call it a parabola. Yeah, so you can say a curvy linear structure, okay, which is higher or which gives higher values of j of theta 1 for lower values of theta 1 and vice versa. The objective, okay, the objective here is to find that one specific theta 1 value, okay, where the j or the cost function theta 1, or you can also refer to as j of theta because theta becomes then a combination of theta 0 and theta 1. And the objective here is to find that one specific theta 1 value, or at least closer to that value. Okay, so I can say find or slash approximate that one specific theta 1 value where j of theta is the lowest in the given context. Okay, so this is the entire exercise that we do when it comes to gradient descent. right? So that is what gradient descent all is about. Okay, so once we plot, as we have seen in the last function, we get something which is similar to a contour plot. Okay, so to show the contour plot, what I'm going to do is that I'm going to share a small diagram. So you need to give me 1 minute so that I can share the diagram. And this diagram will help you understand what is going on here. Give me 1 minute here. I'll just stop the sharing and let me just, yeah, just trying to find the diagram. Where is it? Here. Okay, so let me just take a quick photograph. Oh, very good. Okay. So sorry, just a moment. Yeah, so let me just take a quick photograph of what is going on over here. I've taken the photograph. Let me just maximize this. Let me go back to Zoom. Let me share my screen. And now you should see what is going on over here. So I'll take the black pen. So this is the kind of plot which I get, which is otherwise known as contour plot or a contour figure. Now, how did we get this kind of a structure? Is because I am assuming I am going to have multidimensional data. Okay, so why I am assuming that is because now if I have the representation of contour in context of multidimensional data, then in terms of, let's say, a single dimensional data or I-dimensional data, the graph is going to look something like this. Okay, so the contour plot in 2D looks something like this. It's a curvilinear graph. On the y-axis, you have the j of theta, which is the cost function. And on the x-axis, you have the value of theta 1, because theta 0 you have already assumed to be 0, although it's not going to be 0. Okay, we already know it's not going to be 0. Okay, and we are going to quickly explain that as well, why it was not equal to 0. But this y-axis, imagine, are the values of j of theta, which we want to minimize. So the output of j of theta should be as small as possible. Base is the value of theta 1. So we have to technically find a value which is a value of theta 1 that corresponds to the lowest value. Let's say this is the value of theta 1. That corresponds to the lowest possible value of j of theta that we can find. It is not the actual value. Okay, we will try to find this value. How? Same as what we have done during that that exercise which we did with contour plots. I'm standing over here and I want to get down to the bottom of the mountain. So I take a step, I take a step, I take a step, and I'm taking a lot of steps, and then I'm coming down. Right now, this, if you try to imagine, or if you try to understand this concept, this thing that is happening over here, that I'm coming from this top place to the bottom place, this is actually a kind of, if you look at it from a programmatic perspective, this is an iterative programming. Okay, this is something which is like an iteration that you're trying to do. Okay, so it is similar to the example that I have taken in one of the sessions as well, that if, let's say, you want to print the minimum number out of a list of numbers. So let's say I have a list T, and that T has, let's say, 1000 numbers. I want to print the minimum. Then what do? I first of all, let me take the eraser and remove this. I first of all take a value which is my, okay, my mean. Okay, so let's say mine is equal to 0. Okay, this variable is going to store the minimum value. Then what am I going to do? For any value I in the range of each element of T, so any value I in the list T, what I do, I come inside this brace or this block of the code where I am simply trying to find out, okay, I'm simply trying to find out if my, okay, is, no, sorry, uh, okay, so if my, the value of my is actually greater than the I value, if, okay, if this is the case, okay, that this condition is successful, then I have a new SR value, hence I say my is equal to I. Okay, that's all, right? And that's all I'm doing. I'm not going to do anything else. If I iterate this loop over the all the 1000 elements of this list T, ultimately I will find the minimum value. So this is the algorithm, right? In the same way, you see this is an iterative kind of an algorithm. Why? Because the value of this my variable is changing over each and every loop or each and every step in the loop. In the same way, that is the same thing which is happening here. I'm taking baby steps, and each and every step is iterative towards my final goal, right? So as you can see, this is a bit computation intensive. Okay, that is one of the things that you need to remember whenever you are doing any kind of exercise relevant to any kind of regression analysis. Basis the sample size. Now, in this case, what I have selected as the sample size, if you remember the formula, it is 1 by 2m, right? 1 by 2m summation of I equal to 1 to m, and then my hypothesis function, let me just write it as capital H to save time, and then I have taken a square to nullify the effect of scale. So this m over here in this equation, m is my sample size. Okay, so larger the sample size, I need to be as efficient as possible to design this algorithm, right? We are quite lucky that the libraries that we are going to use to do Python, the regression analysis using some case studies, they already have this implemented in a very nice way. So that is the reason why we may not really need to worry about it. But I have myself seen cases where I had at a certain point in time much lesser RAM in my personal laptop, and I was trying to execute a problem statement where I had uh, data in the scale of a few hundreds of MB. So it's like a 300 or 400 MB data. Although that's not really quite small for the size of a laptop, but then it's not really big as well. I mean, today's data sets, if you see, if somebody tells you he has a data set of 3 GB, it's not really a very big thing for you, because I'm sure all of us has kind of an external hard drive in our home, which is like of a TB of size. So 3 GB size as of today's date is really not a very big thing. But then I tried to write a Python program, maybe I'll share that program with you, to manually calculate the gradient descent. And if I try to manually calculate the gradient descent using plain and simple Python code, similar to this code, right? This is where I'm trying to find the minimum. So kind of similar logic I applied using some other calculations as well. It took a lot of time. Now we are really lucky that when we are going to use packages, and I'm going to introduce those to you, then we are not going to have any such kind of problems because they're already optimized. Let's just try to quickly write down what packages we are going to use. In Python, right, we have seen one method which we have already seen earlier. That method was known as least square method, right? If I try to find least OLS, no, they have not written that, or what? I don't think we have written that. So let's just write down quickly. I think this thing that we are doing over here, right? This is the thing that we were trying to do over here. Point 10, 11, 12. So I'll just quickly write this down. Points 10, 11, and 12 above refers to a method which is commonly applied in any regression analysis, but mostly sorry, this statement is wrong. Any linear regression analysis, and it is commonly known as OLS, or ordinary least squares method, where we come across terms like RSS, TSS, etc. Right? And we were able to guesstimate the values of theta 0, theta 1, and theta 0 using simple statistical measures, right? In these cases, or when we implement them in Python, we would use the scipy.stats package for single linear regression, or I can also say simple linear regression. Okay, or we can use the stats models package for both simple and multiple linear regression. Okay, I'm not sure if I have previously defined this terminology linear regression, so I'll just quickly define it once. If I have three scenarios, which is something like this, linear regression is when my regression line looks something like this. But if it looks like this, okay, can this be a linear regression? The answer is yes, because there is a linear relationship. Okay, but there is no linear correlation. Okay, so that is the reason why this kind of cases are usually not considered. Okay, I'll just take the other pen. This kind of cases are not considered when it comes to linear regression, because irrespective of the value of x, the value of y is always a constant. This is something which we saw when we were calculating TSS, right? So these kind of cases we will not be considering, but these kind of cases where I have a negative correlation or a positive correlation, and we have to figure out how good or how bad the correlation is, those cases are going to be considered as cases for linear regression. Now, there can be other cases as well. Why I'm defining this is because there can simply be other cases where, I'll take an example. There is a small use case in our organization that I worked on, is that the per item price, I wanted to find out if there is any relationship between, let's say, the per item price with the total sales or the total profit that I'm making. So X is my per item cost or per item price, PIC, and this is my total profit. So I'm trying to find out if there is any relationship. What I eventually ended up finding out, just by means of simple ED, I can find this, right? That there is a relationship which is something like this. Okay, it is something like this. Okay, it is going like this. It is going like this. So if I try to plot this, the line is no longer a linear line. I can obviously I can plot a line like this. Okay, but that's not going to be a good representative. The representative line was something like this. So this is not a linear regression use case. This is a polynomial regression use case. Okay, so let me just quickly explain what is polynomial use case. In our linear regression use case, basically we said I have y equal to mx plus c. Here, the most interesting thing to note is the order of x. What is the order of x in this case? I can write x being equal to x to the power 1, right? So this power of 1 is the order of x, right? The order or the number by which I can amplify the value of x without changing the value of x. That becomes the power of x. What if I have an equation which is mx square plus cx plus d? If I have something like this, and this is one of my equations, then I call this equation a second order polynomial. Why is this a second order? Because the maximum power of the unknown x, which is my independent variable, is a square. If I happen to have another equation which is ax cube plus bx square plus cx plus d, then this is actually a fourth order polynomial. Are you able to understand what I'm trying to tell you? Basis that the structure is also going to change. Okay, usually if you see only one bump, you can consider this to be a second order polynomial. Okay, if you see a diagram which is something like this, you see two bumps here, right? So you can assume this is a third order polynomial. You can assume, you can't be sure. I can share you a link where you can see there is a reference or there is a relationship between how the graph looks and how can you identify what order of polynomial it is. Okay, which may help you uh, just as a reference. But the reason why I wanted to explain this is because my price per item to the total profit relationship is no longer a linear relationship. I may want to fit a linear regression line over here, okay, which will look, let's say, something like this, but this is not going to be a very good representation. Okay, I'm sure the R square is going to be very high. So to fit the data properly, this line in this context is really good as opposed to this line, because this line is not good. These are cases of polynomial regression. These are used in the industry, but not as much as linear regression is. When we do linear regression, we will come to know what is the reason behind it. Always try to remember, whatever analysis you are trying to do, ultimately you'll be sitting or standing in front of 10 people, 20 people who have no interest in what kind of statistics you know, what probability books you have read, what visualization tool you have used, which software, Excel or Python or R you have used to create a model, and so on. They are only interested to know what is the business value you are adding as a data scientist, or if the solution to the problem that you are trying to find out or you are trying to deliver is actually delivering any business value or not, which means the people who are sitting in front of you should be considered similar to people who have just entered school who don't know anything related to mathematics. Hence, you need to explain them whatever you're finding is in a very, very easy and a very, very upfront kind of a manner. In which case, if your model is too complex for you to explain, if you have a fourth order, fifth order kind of a polynomial, it is really very hard to explain to a customer. It is really very hard. How do you justify that equation y is equal to ax square plus bx plus c? Right? When we look at the output, or when we actually start coding things up, this will be much more clearer. But it is very difficult for you to explain to people, okay, what is the way, okay, or what is the way in which you are going to explain this, okay, then that really becomes very difficult. So that is the reason why choosing a model which is solving the purpose, as well as it is also helping you to address the business problem or explain the business problem in a very easy way, should be the target. That's the reason why any form of linear regression, simple or multiple, irrespective, is actually far better and far commonly used. Okay, far better and far commonly used as opposed to any kind of polynomial regression. Right. So that is the essence here. Okay, that is the agenda here. Okay. Now considering this in mind, what we have seen here is, now we have a way, okay, to find out the values of theta 0, theta 1. And now we can find out the exact model output. And basis the model output, I will be able to figure out how x and y are actually related. Okay. Even another better example of showing you how this gradient descent actually works is something like this. I'll just do another share and I will show you what is going on here. I hope you can see my screen. So this is a contour plot of multivariable data. This is where I'm standing. Okay, this is my position. Yeah, this is me. I have to come down here. This is where my gift is. If I want to come down here, these are the steps I'm taking. You see, this is step 1, step 2, step 3, step 4, step 5, and so on. So I have to minimize to this value, or let's say I have minimized to this value, and I also need to in parallel optimize this process of coming down. Okay, I can't take the entire life to come down, right? I have to create an algorithm which is also really efficient for me to come down. And then I find out the value of j of theta 0 compared to theta 1. In this case, it is represented as 3 dimensions because I have a simple linear regression problem with 2 coefficients, theta 0, theta 1. Right, so these are the contour plots, and this is the way in which I'm actually coming down to the minimum. As I've already explained earlier, if you remember the class that we had on the visualization, or I believe it was the basics of EDA class, where this point was explained as local minima. Yeah, the point that we reach at the end is known as the local minima. Now, just to conclude this, for any general cases, we can also use in Python a fantastic library known as sklearn or scikit-learn. Right? Now, why not stats models or SciPy? Simply, the statistical packages are open box. That is, they provide all the information they can possibly calculate, right? The package sklearn or scikit-learn, on the other hand, is black box. That is, it simply provides what we need to know as the output of the model and not the internals of the model. Okay, now there is a good thing, there is a bad thing. Keeping in mind, you need to explain the model to people who don't know how or what is the definition of, let's say, modeling. Using sklearn or scikit-learn in many cases is really good. We are going to use that as well, but it's more often than not useful when you are doing a machine learning productionization kind of a pipeline. So let's say you already have a data engineering pipeline by means of which data will arrive in a prepared format where you'll have two columns. One is the size of the house. The second column is going to be the observed price of those houses collected for, I don't know, 500, 1000 houses. The data is scraped out by some kind of Python code or something else from the websites like 99acres.com and so on and so forth. So if you have a data engineering pipeline and you need to add on to it the regression pipeline or the analysis pipeline, you can no longer say that you're doing an analysis, because one-time analysis of the model is already done. You have already identified how to do the calculations of the cost functions and so on. You are simply going to apply a model, and that model should simply be returning you the value of unknown y given a set of values for x, right? So this is the case where I would strongly recommend using scikit-learn, because it is so simple to implement lesser lines of code and so on. But when you are doing the first time analysis of any problem statement, obviously you should start with stats models, because it's going to give you a better view of what is overall happening over here. Now, how do we understand the stats model output is also very simple. When we are going to do practicals, you will come to know that it is nothing but what we have already learned in the basics of statistics and so on. Okay, so again we are going to get back to things like p value, t value, and all these things, right? We have correlation values, we have Pearson correlation values, we have the probability value, which is p value. We have, let's say in this case, one sample or two sample test kind of a concept, because these are numeric variables, and hence we are going to get the t-test outcomes as well. So a combination of all these tests that we have already learned right earlier, the ones which are usually applicable on the numerical data, not the uh, uh, not that we are going to see a chi-square test output when it comes to linear regression, but more of the tests that applies to the numerical data. So those outputs will be there in stat models, and we can clearly see exactly how the model is getting created and what is being considered and what not and so on. So that's the advantage, but that's the advantage for a data analyst or a person who is doing the analysis for the first time. So once you have done the analysis, or maybe it is a one-time analysis task, that's good, right? But when it is going to be kind of a production pipeline, then obviously scikit-learn is going to take an advantage, right? Now, keeping this in mind, our goal is fulfilled. Now we would like to simply find out, or we would like to simply define, okay, we would like to simply define what is actually going on with these values of theta 0, theta 1, and then what we can say about the the importance of these variables. Okay, so to do that, again, let me just try to come down over here, and something that we have already seen, but we are just trying to define the value properly now. So I have y and x like this. This is y, this is my x, and let's say I have some points on this graph. My scatter plot looks something like this, and I have my linear regression line, which I've already found out to be something like this. This is my best fit line. Okay, now Obviously, this is my theta 0, or this is my intercept, right? This is my intercept. And this angle, this slant is my theta 1, right? So this is my slope, okay? What is the meaning of these two things? If we are able to understand the meaning of these two things, we will be able to reciprocate this concept from single linear regression. What we have seen over here is a case of single or a simple linear regression into multiple linear regression as well. So let's just try to write down the equation. Y is equal to theta 0, which is the intercept, plus theta 1, which is the slope, multiplied by x. This clearly means that the value of y, now how to put this into business context is what we are going through. Please listen to this very carefully. If you have any doubts or if my voice is breaking, please put your inputs in the chat box or please raise your hand. The value of y, okay, let's try to do it in a mathematical way first and then we go into practical way. So the value of y changes by theta 1 times x value. Theta 1 times x value is how the value of y changes, considering always a constant theta 0. How do you reciprocate the statement that I just said in business terms? In business terms, you say y is what? Y is my price or my rent. Okay, so the rent of any house can be estimated as some constant or some unknown. Okay, some constant or some unknown plus, okay, some factor, okay, some factor multiplied by the size of the house. Okay, this is how you practically represent the output. What is this factor? This is the factor, okay, which is impacting the size of the house. If you consider this part to be 0 just for 1 minute, then this factor f becomes what? Rent by size. Right? What is the essence of this? By every 1 unit change in the size, for every 1 unit change in the size of a house, there will be this factor times increase in the rent. If I write this down into numbers, let's say rent R is equal to some constant 0 plus 2 of x. Okay, so 0 in this case, let's say, is my assumed intercept and 2 is the slope. This means for every 1 increase, or no, this it should not be R, right? Sorry, this should not be X, this should be the size of the house. So size of the house, if the size of the house is 1 square feet, then the rent of the house is 2000 rupees, let's say. So for one scale or 1 unit of increase of the independent variable, there is this factor times increase in the dependent variable's value. This is how you explain your model. Right? Now comes this unknown or this constant. In any statistical experiment, we have already seen what this constant means. We have just not defined it in a mathematical way. That's why sometimes we have to get back and find the name. We have already defined this as a variable known as confounding variable. There are certain variables which will always impact the outcome where I have no control. Example given in this case, this value of y, which is my intercept, this is a value which is, let's say, something like 50 rupees. We took this example in the last class as well. So let's say this is something like 50 rupees. Why is always a 50 rupees there? If the size of the house is 0, I should not be paying any rent, right? Then why am I adding this constant 50? It's because every time I'm trying to rent a house, I have a higher probability of getting a good house if I go by a broker. And that broker is going to charge me some kind of a brokerage. That brokerage is not this factor. That brokerage is not at all this factor. This factor is something else. And we are going to find the essence of that factor. If you are not able to do it right now, maybe in the next session. But this factor is actually the essence, okay, or the property of this apartment or of this setup of this size, which is affecting the rent. What is a constant or an unknown is something which you cannot avoid. If I am going by a broker, I need to pay brokerage. That's my constant. That is the way to identify the output in a practical context. I hope you got the point. Now, obviously, how can there be one factor and how do you decide that one factor? Let's say I say this one factor is going to be if I have a proper road in front of my apartment or not. So let's say this is my apartment. Do I have a good road in front of me? If I have a good road, obviously people will buy cars and people will be able to drive quite easily to and fro, and that will increase the standard of life. If that is the case, then clearly the value of this house is going to increase. You have already seen this in the cities where you are already living. The rent of houses, which is in posh areas is where roads are really very good. If roads are good, the rent increases by default. Okay, why? You have a very good road. Okay, the broker is going to say, see, sir, how good the road is. Try to imagine if that is the only factor in which the price of the house is going to increase. I don't think so. It can't be the only factor in which the price of the house increases. The price of the house will be dependent on how good the road is. Is there a school nearby? Okay. Is there an ATM nearby? Okay. Is there a medical shop nearby? Very important in these days. Is there a hospital nearby? Right? These are the kind of multiple factors which have some effect along with the size of the house. Along with the size of the house, it has some effect, and then it is giving me the rent. Now, these cannot be considered as factors because all of them are going to have their individual values, right? All of them are going to have their individual values. If I'm going to create a data set, let's say, a kind of an imaginary data set. Is there a hospital in my area? The answer is yes. If the answer is yes, I'm going to write 1. If the answer is no, I'm going to write 0. The answer is yes, hospital is there. Okay. How much distance is an ATM from the house? Let's say it is 500-meter distant. Okay. Near to the house, just by 500 meters, I have an ATM. How much distance is from the house to the school? Let's say it is 1 kilometer. So it is 1000 meters. Right. Is there a road or not? Is there a proper road available or no? The answer is yes. Is how much distant is the medical shop? The medical shop is, let's say, only 100 meters distant. Then what is the size of the house? The size of the house is, let's say, 750 square feet. Okay, that's the carpet area. A combination of all these variables is actually a more practical way to represent what is going to be the rent of the house. This problem statement is known as a multiple linear regression, or it is a multiple regression use case, because we still don't know whether the relationship is linear or not. We are trying to find a model that best fits the linearity. We may or may not be sure or confident if it is really linear. We are going to find that out. Okay, this is multiple linear regression. Now, some factor will be affecting the presence of hospital. Some factor will be affecting the presence of ATM. Some factor will be affecting the presence of school. Some factor affecting whether there is a road. Some factor affecting whether there is a medical shop. Some factor affecting what is the size of the house. All of these factors are now going to play a pivotal role in the calculation of my equation. And that is the reason why I can no longer have my life simple, and I can no longer write an equation which is something like this, or otherwise theta 0 plus theta 1 x. I have to evolve. In real life, I need to evolve. How do I evolve? I evolve with a function which is something like this. I equal to 1 to n, where n is the number of features or n is the number of factors, like whether I have a hospital or not, how much distance is the ATM for. So those are my independent variables, number of independent variables, not the sample size. Let's say the sample size is still m. N is the number of features we have. I need to represent this as theta I xi. Okay. Added to this will be some constant, which I can never get rid of. But if I consider this constant to be almost, let's say, approximately equal to 0, then this becomes my simplified equation. This is not as simple as I have just explained. There are many more complexities. It will take some time for me to explain this. Hence, let's make a stop over here. I'll stop the sharing. I'll clear the drawings. If you have any doubts, please do let me know. Yeah, let's try to discuss again. And if you have any doubts, please let me know. Let's call it a day. Thank you.
Thanks, Bhaumik.
Good
Good
night.
night.